Are you in office or at home?
Yeah, I'm in office, so we're not allowed to have meetings, but like if like for these kinds of for teaching, we're allowed to go here.
Oh,
Yeah, of course. Our numbers are really getting through the roof in Austria. So there's like lots of.
I think we went through, I mean, there were 2 months of very typical Singaporean style lockdown. So those were, you were not allowed to meet anybody who does not live with you in public or in private for 2 months. But now numbers are pretty much in control.
Now they open schools again on Monday, which is completely strange, actually. So I don't know why they did that. And in Germany, they're like always like 2 weeks behind. It seems they're going to do complete lockdown soon.
Wow. So I'm waiting for Supratik to make you host.
Can I do this pop in thing? Ah, yeah. Cool.
Hi, Kuldeep.
Yeah.
Yeah, so it's working fine.
Okay. So
The
I think, can you also make Armin co-host?
Yeah, I'll make our.
I think that will.
Yeah, Armin is also co-host.
Okay. So
Mhm.
So, Armin, are you
Yes.
able to control the mute, unmute, share your screen, and all of that?
uh,
Okay. Let's see. Share screen. We try.
Just in case if you wanted to do that, if you wanted to mute somebody here.
Ah, you mute somebody. Okay, I see. Oh, but usually if I share screen, it's you don't see the participant thing,
Yeah.
so it's actually
So,
difficult to.
so
So I can only stop sharing and then do the thing, right? If you want, but
I
was
guess it
so
should not be needed because I guess Kuldeep also has that control. I also have that
okay.
control.
yeah,
Just in case you wanted to have that control.
yeah,
Oh, well,
yeah.
I hope people behave.
So I mean, if there are questions, then I'll kind of at some point try to stop you, and
Yes.
you
So
won't
how
be
do we
able to
do?
see this
So how do we
screen.
do it with the questions? So I'm happy if people would just unmute themselves and ask questions, or if you wanted wanted to go through you, that's also fine. So the yeah.
Okay, I guess yeah. At the start, you announced that you can just unmute yourself and ask questions. We are fine with either,
Okay.
whatever works best for you. But if I see some questions, some people
Somebody
Mhm.
puts
just
it in the Zoom chat window. Maybe Kuldeep can.
Yeah, exactly. Because
Uh,
I won't see that. So then maybe Kuldeep then has to stop
yeah.
me. Okay.
So Kuldeep will be monitoring that, right?
yeah.
I mean, I can also be monitoring that.
Yeah.
Maybe both of us will monitor.
Mhm.
Okay, so I guess we are 1 minute from the announced
Yeah.
time. So Kuldeep, your microphone is again in the wrong position, or is this the right?
No, apparently this is how it's supposed to be used.
Is it okay?
Yeah. So, Armin, I got this microphone on, although now I think bit of advice, and then it setting this up required more effort than I guess the quality improvement. So marginal utility of the phone is fairly low. Okay, so I guess we can start, and probably I'll uh, maybe another minute.
So Armin, if you could
Yes,
share your screen, if you
yes.
could share your screen. Okay, great. Yeah, yeah. I guess you could go back to the video.
Okay, so let's get started. Good afternoon, everyone. We hope you had a good lunch. So, welcome to the first plenary session of SAT+SMT Winter School. And it's my great pleasure to introduce our speaker for today, Professor Armin Baer. Professor Baer is the chair of Institute for Formal Methods and Verification at Johannes Kepler University in Linz, Austria. His primary research interests are applied formal methods, more specifically formal verification of hardware and software using model checking and related techniques. He's very well known in SAT community. The decision procedures that have been developed by him and his team regularly have won awards at international SAT competitions. In fact, he has won over 60 medals, including 37 gold medals. In last few years, this is a typical practice that gold medals are set for his team, and rest of the competitors compete for other medals. He is also recipient of IBM Faculty Award in 2012, received the TACA's Most Influential Award in the first 20 years of TACA's. In 2014, the HVC 2015 Award on the Most Influential Work, um, ETAF's 2017 Test of Time Award, the CAV Award in 2018, and recently at ISCAI JIR 2019 Influential Paper Award. So we are very lucky that Professor Baer could agree to speak today. We would have very much liked it to be in India, which we hope he'll be able to come once situation normalizes. So over to you.
Oops, sorry. That was. Can you hear me?
Yes.
Okay, so thank you very much for the invitation. And as Kuldeep said, I plan to come to this winter school for a long time, but there's like a conflicts with one of my daughter's birthday. And so this year I accepted, and even though it's very close to the birthday, and I thought like to be now in India, but unfortunately I'm not. So that's like how life is. But anyhow, so it's a great pleasure for me to give this talk. So let me just say that please interrupt anytime. The only issue is I won't see you if I share screen if you ask questions, but nevertheless, please just try to unmute you if you have questions and interrupt me. Okay. And otherwise, what's also possible is just write it into the chat. For instance, if you don't have a stable internet connection, then the moderator Kuldeep will ask the question on your behalf. Also note this is recorded, so everything you ask and what I answer will be kind of on YouTube, as I understand. All right. Then to the organization of this talk. So I just gave like another SAT tutorial at the CPIOR conference in late September. And I took, of course, some of these slides, actually most of them, but extended them by preprocessing, which I removed. So my plan would be now to have this very dense talk from CPIOR extended to 1.5 hours. So this is our first session, and so it's like 50% more. But it's lots of material. But I still would like you to be interactive. So if you have any questions, please interrupt me anytime. Then for the next session, I would have the preprocessing, which I gave in different forms and updated a couple of times before. So actually my first tutorials, maybe in 2006 or something, were all about kind of preprocessing. And but lots of things happened. I'll sort of talk about the latest idea there. And then at the end, the last hours, I'm really looking forward to that one. So this is why these 4 hours give me the opportunity to really go through some code and answer questions, maybe sort of more on the whiteboard. So I have a virtual whiteboard here. But ideally, I will start with explaining software, both KISAT and Cadigal. Of course, like I could talk about this for days, but we'll have 1 hour. And I'm really happy if you would ask some questions, if you looked at the code. If not, I will do a gentle introduction, also explain the testing framework, which I think is quite interesting. So that will be the last hour. All right, so let's move on. Okay, so my favorite slide is this one. I hope not I hope not all of you have seen that before. So this is my introductory slide to SAT, and even for those who know this by heart. So I was told by the organizers that most of you already have seen quite some material on SAT. This may still be slightly interesting for one particular reason. So you will see that when you go through the example. Of course, you have all these operators, and then all our variables tie and shared are Boolean, and they can be true or false. And then the question is, what should I word today? And all right. I do have constraints, of course. These are just a sec. I need to get my fancy pointer here. So here's like a constraint which says clearly one should not wear a tie without a shirt. Then there's a second constraint here, which is not wearing a tie or a shirt is impolite. And then we have wearing a tie and a shirt is overkill. And these three constraints are then encoded into logic, like you see here on the right. So this is an implication. If tie and shirt, this is one of them has to be true. And this is kind of the typical third type of constraint, the mutual exclusion. Tie and shirt should not be true at the same time. Okay. And what's now the interesting part? Well, if you think about it, these are a set of constraints which restrict your choices. And of course, that's very natural then just to conjunct them. And in the bottom, you see a CNF. So in a certain sense, maybe humans actually work with CNF in this, because you have these constraints which tell you what to do. Actually, they tell you what not to do if you think about it, right? So these all are ruling out one not nice or one thing you don't want to do. So each constraint rules out exactly like one situation, like the last one down here. This rules out that shirt and tie are both true, right? This rules out that both of them are false, and this is another condition. Okay, so I want to argue that even in this simplistic example, you see that CNF, what this type of formulas, you have the bottom with conjunction and then clauses. These are these OR constraints, is quite natural. And then typically the other thing I want to show with this example is it satisfiable? So that means what do I'm wearing? Well, what I'm wearing here is a shirt but no tie. So that's exactly the solution of this CNF. And then the third thing is, are there other solutions? And they're not, right? So because each constraint down here rules out exactly one solution. And there are 4 solutions, 4 assignments to tie and shirt. If I would now add here this third one, which say not shirt, right? Then I would rule out also the last possibility. And that would then make the formula unsatisfiable, and the SAT server would say unsat, right? Okay, why I'm here? Well, cool deep set this. So this is from 2015 actually, where and it's also not all the medals. So I'm not doing much on this. So this is brand new, and maybe it's actually also a good thing to ask questions if you're interested before we go into sort of the technical material. So we produce this. Oops, here's my mouse pointer. We produce this plot after the SAT competition. So Marijn helped me to have this fancy Lua plots he's doing. And but I had this material prepared earlier. So what's that? Well, what you see here is a cumulative distribution function. We recently moved from cactus plot to these distribution function. And if you want, we can also talk about that. But let me first explain what these are. So on the x-axis, you see the time, and then on the y-axis, you see the number of solved instances. And of course, solving more instances is better. So that's why this orange curve here, which belongs to the solver QSAT here, is best. And who's worst? Well, it's this solver here at the bottom. It's called Limat. It's actually also by me, but it was winning the competition in 2002. So all these lines correspond to winners of all the competitions since well, this happening in this century. There were like 2 competitions before in 92 and in 94, but for those we don't have any source code. And also here, it was actually the most difficult part was actually getting the source code running. And so what I did was trying to get hold of this old source code. So I saw Mate Sos actually in the chat. So I also had issues with his version. And so you really have to, even 10 years back, yeah, we really need some effort to get this thing working. I also do have now legacy software like even earlier, like CRASP and ZChef from 2001, but this was even more difficult to get
So
working.
I have a question.
Yes, please.
These graphs here, I mean, you have dates. Okay, those dates are the dates in which that tool won the competition that year. But these are all a comparison when you ran it now at 2.
Exactly. So that's what I wanted to say. So you want to have a sort of apple-to-apple comparison, and because of that, I had to port all the source code because some of these solvers like would not accept anything above 2 gigabyte, which needs to more than 2 gigabyte. But nowadays we have the competition. Actually, this year had a 24 gigabyte main memory limit, but the organizers made a mistake and allowed 128 gigabyte. You see, this is substantially more than back in the old days, because most of these solvers were done in the 32-bit age. So I had to port them to 64-bit and also fix some memory issues. I mean, like really bad memory issues, things like which would only show up if you're like an offset, which in the code was 32-bit and was a delta between 2 pointers, right? But when you move to 64-bit, you have to change the source code to have this offset be 64. But they also don't show any discrepancy. So when I first ported it, like there were bugs, of course. But these bugs had all to do with parsing or with the parsers are actually the things which break easiest, and then also with these 64-bit issues. And then I was compiling this on our cluster, which I don't have, which is almost the same speed as the competition cluster, slightly slower, 10% slower. And then running these kind of old but fixed software on the latest, like this year's benchmarks. I have this also for older competitions, by the way, if you're interested. So if you go to the KISAT homepage, you will find also plots for benchmarks from 2019 and also from 2011, which is kind of half in the middle here, right? So we have here glucose winning in 2011, and that's why we also had the data for this year. If you go to the web page, then please be aware that in 2000, like here, there are 400 benchmarks actually in the competition. I don't write this anyhow. And these over sort of like almost 250, so slightly more than half, while in 2011, there were only 300 benchmarks, and actually also the solvers solve around like 250. So it's way closer to solving almost all benchmarks, and there of course it's much more difficult. So here's sort of more sort of like we cannot reach solving all these benchmarks yet. Yeah, and of course, like if you're interested, we can also maybe later discuss more details, like interpreting this thing. But it's not that easy. But also, let me point out. So this is also why I put here the pencil that actually crypto minisat and maplesat would be around here actually. So even those two would be leading the past solvers by quite a fraction, and this distance here, for those of you who are interested, is like kind of local search. But I won't talk much actually in this tutorial of that. All right, so let's move on. I have here also like some tweets on this, and I'm pretty proud that there are lots of people shared this and likes this. So this is it seems like how you do science these days, like over Twitter. And the other thing here on the right I want to point out here is another tweet, but it's related. This is from a issue from Bulector, which is our SMT solver. And Bulector was used here in this bounded model checker from Oxford, as ESBMC. And they were using it on deep neural networks, as you can see. And then they used like one of my older solvers, Lingeling, actually, because this was the default in Bulector like a couple of years ago. And they seem to use still the old version of Bulector. And well, it hits like 2 to the power 27 variable limits. So the library says, okay, I cannot handle more than, like, says sort of like a roughly 128 million variables. So that means people are really using these solvers here for really big things. So like really millions of variables. And maybe that's also something you might want to know, that is actually, this is the sort of the latest reason for doing KISAT in this year, and last year and half a year. It's because like we're getting bigger and bigger instances, and there's kind of now a very strange situation. So these old solvers, which are really compact, so Lingeling uses like 1/4 of the memory than other solvers, they hit the variable limit, right? And they're doing this, I think probably on at least 128 gigabyte machine, probably larger, because otherwise you cannot reach that limit. But if you would use another SAT solver, like minisat, it would use like 4 times more memory. So then you would need a half a terabyte machine, and actually to get to the point where Lingeling gets, okay? And this was kind of the reason for revisiting what was done in Cadical, which was my previous solver, which is like slightly better than minisat, but same range of memory usage and all the other competitors, actually, like all these Maple solvers. And implement a solver which uses far less memory. And in practice, it's in the range between sort of 1/4 and half of the memory of the other solvers. Okay. So this is the handbook. Where actually, if you haven't seen it, here's a real version of it. So it has a nice design and all like that. And all these black dots there are chapters. These chapters here, and this is from 2009. And we have kind of split it in two parts. And in these 10 years, actually it's now 12 years, lots of things happened. One thing which happened is here in Trento. This was in 2012, where Donald Knuth got involved in the community. So here's Marijn Heule, here's Shao Marquesillo, in case you haven't seen it. This is me, this is Holger Hoos, Carsten Zins, Fahim Bachus, and then well behind Knuth hidden Oliver Kuhlmann, Roberto Sebastiani, and John Franco. So like kind of hardcore core people of the SAT community were there, and Don Knuth gave a talk. And the reason he gave a talk was actually this book here. He wanted to write, and down here it's satisfiability, right? Can you see it? And it has 310 pages, but it's actually only a section, okay? So it's a section C7.2.2.2.2 actually. So he's writing a section, a subsection of size 300 pages. And he wanted also, so there's also part on conflict-driven clause planning. So that's why Knuth here actually visited us here in Linz, gave a talk. We took him also to the Anton Bruckner organ, which is close by. This is like one of the most famous organs in the world. So he played that one. And then finally, this book happened, like there are PDFs on the web, and you can look it up. Now, in the meantime, there was people were really working on SAT. So this was actually the biggest worry of Don when he wrote that book, that sort of like SAT will just sort of continue to produce lots of materials, and it did, even though some of these chapters you see here, which we're going to have in the second edition, and we're really in the final stages of this, so it should appear within the next month. And we have 7 new chapters, like one on proof complexity, and one on preprocessing, and one on tuning and configuration. So these 3 chapters were already in the planning for the first edition, but it didn't make it. And also, like back then, for instance, for the preprocessing chapter, we didn't really have that much material than what we have today. So the proof complexity chapter is the largest edition. So I think like it has 120 pages. Then Marijn talks about proofs of unsatisfiability. There's a new MAXAT chapter here, and which is more like the novel state of MAXAT is, as you know, all based on sort of core-based approaches, and that's why we asked additional authors to do this. And similar here with the moderator as co-author, well, both moderators as co-authors. We have also approximate model counting, because also there was a breakthrough in 2013, and that was not present in the old book. And similar for the QBS, where suddenly since then we had like this work by Mikolas and also by Olaf and Florian and Martina on proofs. Okay, so we're really looking forward to this new edition. There are also quite some updated chapters actually. Like the CDCL chapter is, for instance, completely rewritten, so it's completely new. So Joao and his co-authors took quite some effort. And we got also like a quote from Donald Knuth, and I can reveal this already now. We also recently got a quote from Stephen Cook, because next year, when the book will appear, it will be 50 years of the proof for the MP completeness, and that's why we thought, or we thought like a quote by him would be also good. So we have 3 very renowned researchers on the back cover. All right, this doesn't work. So now technical. Is there any questions on the history thing or on this handbook? Otherwise, ask later. Um, I'll I'll I don't know whether I thought like I keep this encoding part because it's less taught, and I think it's very important actually to teach also the encoding part, even though it's not directly SAT solving. But on the other hand, it's also not true because you can use SAT solvers out of the box. But first of all, you need to know how to encode things, and then also there are variances, and you need some understanding how to encode things. Like SAT solvers, as I said, are robust, but in principle, it's still possible to do mistakes there. So that's why if you're using SAT solvers, you need to think about encoding. Then in the middle there, we have preprocessing. Preprocessing would only be kind of downward here, but later when we go preempt search and go back to simplifying the formulas, then we'll call it actually in processing, which is actually the how SAT solving is actually doing preprocessing these days. So you kind of interleave search and preprocessing, and that's what we call in processing. And I could have written here preprocessing if you want. There's also one part which is kind of interesting in software engineering, actually pretty difficult, but some people worked on this. Yeah, actually also Kuldeep and also Mate. But if you have a CNF, maybe sometimes it's better to re-encode things. And but of course, you can also interpret this as kind of in processing. So but I like to think in this way as a re-encoding, and you see one example here in this talk about that. All right, so this is my favorite introduction to that. Like for people who are have more software background, well, you have like an original C code on the left and here, and you have some optimized code here on the right. And then you first think, why do you come up with such a complicated code with all these knots in it? Well, what happens is you write like a simple version, which might have only one if and else. And then you're testing it, you find a bug, and then you would go back to changing it because you missed the corner case, and then you add this corner case, and then things get complicated. All right, so this is why you kind of end up with this messy code here on the left. This is typical, but this code here on the right is kind of better. So it's kind of a form of refactoring. So when you came up with this one, you might want to finally get to that one. Now you think about you would have an IDE like Eclipse, and it would be possible to open two windows. And on the right hand side, you have this optimized code. On the left hand side, the non-optimized code, and then you want to sort of highlight both. And then tell the IDE check. And how do you do that? How do you implement this? That's what I want to say. Well, the trick I used here was I'm going to use these H, T, and F and assume they have no side effect. So that means also evaluating these expressions A, B should have no side effects. Therefore, I can model this effect of H. Sorry, they should have side effects, of course. The only effect they have are side effects on the global state. And FTH would just be modeled as a Boolean variable, either 0 and 1. So they can all independently be 0 and 1. And this shows that it matters which of the three you actually pick. And then the A and B, they are just sort of Booleans, and I keep them as that. Now, I can take these two, right? So like here we have the original one, which is this upper part here. And the optimized is the other one. And you need to compile this sort of, and that usually always happens. And now here compilation is pretty simple. After I make this trick by abstracting the side effect of F and G and H as a Boolean variable. And then I want to show that origin is equal to optimized. Instead, and that's, I'm not going to explain this in detail here, but it's a very important step if you haven't seen it before. And of course, like we're doing first semester course on logic, and we teach this all the time. So instead of checking that they are the same, we're actually doing the opposite. So we do a kind of refutation proof. And how does the refutation proof work? Well, we assume they're the same, but we negate it. So this is why we put here an equivalence between the two Boolean expressions and negate it. And the result of that is that if this formula is satisfiable, it presents a counterexample to the that these two functions are the same. If they're it's unsat, then there's the same. All right. The same is for hardware. If if some of you, I hope, are interested in hardware too, and this is where this actually also came up first. So you have this a pink or violet circuit on the top, and you have this yellow circuit here at the bottom, and you want to know whether they're the same. If you look closely, they are actually just, I don't have it on the slide, but maybe I'll write it. So what you're really doing here is A or, sorry, no, I got it wrong. B or A or C, right? No, sorry, A or B. Let's do the top one. The top one is B or A and C. Yeah, I had it right. And that's the same as B or A and B or C. So this is like a distributivity law, but one like the dual one you would know from arithmetic. So in arithmetic you would only have A. Sorry, it should be with the B's. B times A plus B is A plus. Sorry. C, BC. All right. And the one with and with the sort of a plus here and A times C here, that's of course not the same as B plus A times B plus C. So for those of you already like a little bit advanced, you can think about whether this is true for if we put here an XOR. Right, so this is XOR. Okay, anyhow, so this is sort of the semantics, but how do you do this completely syntactically? Well, you would just take these two circuits, you put an XOR at the end. This is called actually a mitre, and I have a long story about that, but I don't repeat it here. And then you have this a circuit which produces at the output O here, true if these two circuits, if it's possible to distinguish these two circuits by finding values ABCs that they're different. And how do we get this now into SAT? Well, SAT solvers, as I explained already in the introductory example, work with a CNF, and therefore you need to get this into some sort of a compilation into a circuit, and then from this circuit into, which we have already in this example, but in the previous example, the software example, we had to interpret the software as a circuit. And then the second step is getting that into a flat CNF, and the trick here is very interesting. So you, for each internal signal here, we're introducing a variable xuv, and also for these guys before the mitre, these are the original outputs y and w. All right, and then we say we relate this x here to its inputs, which you can hardly see is a and c, right? Okay, on the right hand side, you see there's x is equivalent to a and c. So this is very sort of like simple task. So you take, you first introduce sort of helper variable, auxiliary variables for each thing you compute. Okay, so x, u, v, y, and w, and then you add local constraints for this computation, for this local computation, right? So on the right-hand side, we just say x is equal to a and c, and so on. And here, for instance, we have O is equal to y, x or w. So that's very straightforward, and you can already see this is kind of a linear algorithm. And that's like one more thing here, which might be a little bit puzzling. So this is my favorite question. If I ask the students in the class on SAT, why is there an O here at the output? Well, we also need to sort of query. So you can think of sort of this as the database which tells you what's going on. This is the semantics of the model. Like that's what the world is doing and what you're modeling. And this is a property, right? If you think in natural science, well, no, I'm not making this analogy here, but like this is the idea. So all these constraints down here model what the execution, and this constraint, which is trivial here, is your property. Your property is, well, I want to make these outputs different. Okay, and then what's remaining here to get this into C and F, something the SAT solver can accept, is just encoding every line here individually, because we have already an AND here, okay? And every line here, let's look at this X is equal to A and C. Here, that's I do this manually by splitting it. But for those of you who did a digital design course, well, you just do sort of a two-level sort of cardinal map thing, or sort of espresso. So you just take a circuit and you take a Boolean function, which in case this is such a line, and you produce kind of the products of sum. So which, and it's exactly the dual algorithm for sum of products. And then we can do this also for other operations. So here's like negation on top, and maybe the simplest one I have not touched here. So this is maybe equivalence, right? So if X is equivalent to Y, how do you do that? Well, it's plus X implies Y, and Y implies X, and that's the same. Or let's do equivalent as not X or Y, and X or not Y. Okay, and then the more complicated one here at the bottom, here we have that a gate, right? The output of a gate is X, and it has two inputs, Y and Z. And then the gate computes whether these two are the same. So you could call it in hardware a comparator. So we saw the AND before in detail, that the same exists for the OR. For this a more complicated one, you actually need, as you see down here, more clauses, 4 ternary clauses. And next slide, you will see the ternary, like the max, the if then else has the same situation. And let's look, for instance, here for this first clause. So this says if so you need to do now the implication encoding and De Morgan here in your head. So this says if X is true and Y is true, then Z has to be true. Okay, so if X is true, the output is true, okay, and one of the inputs, Y, is true, then the Z is true. Of course, you can also read it from the right. So for instance, if you look at this one, so this one says if Z is false and Y is true, then the output X has to be false, and so on. So it works in the same way as we saw for the shirt and tie problem, right? All right, so this finishes our Boolean encoding of circuits. Now to something more complex, and that's how to encode word-level problems. This leads to this concept of bit blasting. And actually, bit blasting is really blasting. So so we have, for those the more advanced people here, if you take the logic in SMT lib QVFBW, which is arguably the most important one, this is actually next time complete. And the reason for that, so we showed this in a couple of papers a couple of years ago, and the reason for that is because this bit width, which we kind of write down here, is in a certain sense encoded logarithmically in the input, right? And if, for instance, I write like 1024, like the same thing with 1024, and sorry, I would not do it like that. So I would write it up here. So I would say 1024, 1024, 1024. Then you see this is very small text, but of course, if you think about this adder here, well, this adder has actually lots of XORs in it. It actually has like 1024 XORs in it. And therefore, bit blasting is this translating this adder here, this here would require then 1024 in this example above. For the example here on the slide where we only have 4 bit, it's like 4, 1, 2, 3, 4. And we instantiate here this adder, full adder 4 times. And we need 2 XORs. Actually, it's 2 times 2004 XORs. And then the output of this full adder, which is the second part here, this is the output here. This is the output carry. That's just a majority gate down here, which says at least 2 input bits are true, right? At least 2 input bits are true. And it's symmetric function. It says X and Y is true, or X and I is true, or Y and I is true, where X and I are sort of the 2 inputs bits you adding, plus the carry in I here. Okay, so this is how you get like from an equation here on top to CNF. Actually, not completely. So the bottom here, you only see a circuit, and then now you still need to get from the circuit into CNF. But for that, we'll just using this stating transformation we discussed here. Now, if you put this into like an SMT solver, like a bit vector solver like Bulector, you would get actually already something complicated. So what you see here is a very high level view of what Bulector is doing. So it has like a parser, which is always like a pain, and it's like for SMT actually even more than for other things like a beater or and then you need to translate this internally into expressions. So you have kind of an expression library. And this expression library has already some optimizations, which I don't explain here. They're kind of bottom-up simplification. We'll see some of them later in the AIG I explain. But then you would also do, and that's a very important part here, this O2 optimization. So what's O2? Well, O2 means usually you're doing a global optimization, so you need to sort of collect some global information before you can apply this optimization. While this O1, which we discussed before here, so this one here, this really is like local. So you only look sort of maybe a bottom up while you're constructing terms, whether you can simplify the term you're constructing by sort of looking at the children, but only at the children, maybe at the grandchildren, but not further down. While the substitution here is really something global. So you're looking through all the constraints and you try to figure out whether you can substitute some. And this is very important because in many encodings, particularly if you encode software, or if you go back to our example here, you see this already partially. So this you can see as equations that X is equal to this, Y is equal to this, and so on. But for software, it will be the same. So if these are not AND gates, but these are sort of program statements of a programming language, then you would do the first step, also get like a single static assignment form where you have for every computed statement, you would have a new variable, and then your encoding into this part here would be exactly the same. So each constraint would be listed here. And then it's best to first do a global substitution to get back a real circuit, like a DAG, like instead of having this list. And this is done sort of in this substitution here. Right, and then there's some more, which I don't have time to go in that, but they usually do not, the normalization here for arithmetic would do it, like it would keep the models, but slicing would, for instance, maybe not keep the models. And then after these global optimizations, you get new expressions, then you synthesize them, as we just saw for the adder. And then we get as output a circuit. In this case, we're going to use AIGs, which is the next topic. Then we can optimize these AIGs, which I will not talk about here in this lecture. And then we'll get like an optimized AIG, and then we do our stating encoding and get to CNF, which we then can give to a SAT solver. Actually, in Bulector and in most of, except for C3, bit vector solvers, and also not STP, Cadical is now the default SAT solver. Okay, so what we're having here is like we're having application levels. You saw this like a little bit for hardware and for the simple software. And then we're going into bit precise semantics, which would be bit vectors. And then from bit vectors, we go to a bit level representation. Usually we use AIGs, but there's like also alternatives. And then from that, you go to CNF. And the reason why you cannot jump directly from 1 to 4 is because like on each level, there are optimizations you will miss if you don't have that level. So for instance, CBMC didn't have this 3 for a long time, but you're really missing sort of an optimizations if you don't have a circuit, a bit level circuit representation in the middle. I will also talk briefly about logical constraints. All right, so once again, these here on top, these kind of model how a real system is executed. And then you need properties and maybe logical constraints, which are on top of that. So remember the O unit clause we saw before. Okay, so I'll go very fast on these AIGs. If you want to know more about those, I can elaborate. So these AIGs are sort of a very simplistic circuit representation where you only have AND nodes, like these big circles are AND nodes, and these dots here are negations. And of course, like you have variables and maybe also constants. So what you see here is actually an XOR. Was there some, I heard a noise? No, no question. All right. And you can convince yourself that this is the XOR by doing this kind of demarking thing here. Like this, each line here is like one black dot. Now, here are 4-bit adders, like the thing we saw before as an AIG. So if you would just take the description I did before, you wouldn't get that one actually. Here's this gate here, which is shared. So this is, you see, this guy here is actually an XOR. If you would go back to the previous slide, and also this here is an XOR, and down here is another XOR. But you kind of need to have this these 3 guys, they make kind of the carry out of this stage, and they share a gate of the XOR. In order to get that, you need to do some circuit optimization or like a clever encoding. And the same is true here for this 8-bit adder. And you see this is just twice as long as this one, and you can imagine how this would look if you go to 32-bit. So you're probably watching this now on a 64-bit machine. So this will be 8 times larger than the 8-bit adder. So for every addition in your program, which you want to sort of check with the SAT solver, you would need to like 8 times larger circuit. So this is a shift operation. So this is called barrel shifter. The interesting thing about this is like shifting 16 bits here at the bottom. And here are the shift amount. The shift amount is only 4 bits. And you see that the height of this barrel shifter, it's called, is actually logarithmic in the bit width. Okay, so if you do this for like 32, we'll just add another layer, but it will just be 5 times 32. And you can do this also for 1024 then, because it will be 1024 times 4. All right. Next example. So this is an 8-bit multiplier, and multipliers are actually quadratic. So they're not exponential, but they're quadratic. So the encoding of a multiplication of a nonlinear constraint in bit vectors is quadratic, and you cannot get away with this. And of course, like you could do this for 32-bit, or you could do it for 1,000 bits. Like for 1,000 bits, you would end up maybe with a million gates. But of course, you cannot hope that the SAT solver can sort of really work with these, because otherwise you could actually break RSA, because you could factor really large numbers. So even if you can represent like this 1 million gate circuit in a formula, this particular circuit will not be sort of like solved by a SAT solver if you put like certain actually constants at the output. Okay, now let's have a brief detour on logical constraints. And there's one thing which also only if people are interested, I will elaborate. It's this least versus largest fixed points. In many sort of like formalisms, for instance, sample logic, you would have greatest fixed point, least fixed points. You would have kind of equations which look like that, and they're kind of recursive. You read this as a really directed equation. So x is computed as a or y, and y is computed as b or x. And of course, this computation is then recursive, mutually recursive here. And then maybe in your logic, you would have an explanation what it's really semantics. And often it's like least fixed point or it's like biggest fixed point. And the interesting thing is, this looks like almost like you could encode it directly into SAT, right? Just take the setting encoding of these two gates and that's it. But this would not work because it only can capture actually largest fixed points. If you want to do least fixed points for this thing, like largest fixed point would, for instance, be here, the solution would be that x and y are true because it's naturally just satisfies both constraints. But if you're interested in the least fixed point, then the semantics would be that x and y have to be a or b. And that's not enforced by the SAT, so if you just encode it as is. If you really want that, you need like a different semantics and actually something which is actually more difficult than NP or co-NP, and that's actually implemented in this ASP solvers, which have these stable semantics or stable models. So if you're interested in that, Google for answer set programming. Oh, I should write this down here. So this ASP means answer set programming. And of course, they're using also SAT solvers, but they need it like this. They use it in a similar way like SMT solvers would use SAT solvers. So like as an oracle. Okay, what we're now going to do here is cardinality constraints. And for example, so this is one constraint. And cardinality constraints were that, well, they look like that. So you have like literals like L1 to Ln, and there you want to bound how many of these literals are true. So in this case, you want to give a lower bound. So K would be a constant actually. K is like maybe 4 or 5. And you want to say that this sum is larger than 5. And you can also make it smaller, or you say it's equal. So you can think of this as linear equations over these Boolean variables where the coefficients are all just sort of 1. There's an extension of that where you also allow coefficients which are numbers, and that's called pseudo-Boolean reasoning, or 0-1 ILP, if you heard about that. But I'll not talk about that further. So how do we encode such a cardinality constraint? They actually occur quite often in the real life. And yeah, my third explanation here is this one. So this goes back actually to Shannon. So it's very old, like more than well, almost 100 years now, 90 years it's old. And what you see is actually BDDs. You might not recognize it as a BDD because I kind of turned it around. So you need to kind of turn this and move it downward in order to have it like look like a BDD. So the leaves of the BDD are these 0, 0, 0, so the 1, 1, 0, 0. And these are just like if then else or maxes, like usually in a BDD, you would take a decision whether L1 is true. If L1 is true, you follow the solid edge. This is sort of the common graphical notation for BDDs, you go downward. If L2 is true, you go downward and go to L3. And if one of them is false, you go to the right? So like, for instance, this path here, would, which are like one right, one down, one right, one down. That would be L1 false, L2 true, L3 false, L4 true, and so on. And then you just need to sort of think about what does this constraint here at the top say? Well, it says that 2 of them should be true, but not more than 3. So that means if you go down only one step, okay, and then the others are all false, well, you should remain false. Of course, if all of them are false, it's also false. So at least you need to go down twice, and that's this row where it's true. Also, if you go one more further, it's true. But if you go one step further, like 4, like if you reach like this line here, then you're sure that 4 literals are true. Then this constraint is falsified. Yep, and this is kind of a simple way to do it, and sort of for small case, even still probably one of the best ways of encoding constraints. At least like it's incremental, for instance, and all right, so I want to end this encoding part with this example, which is quite intriguing. I learned this actually from Niklas Ehn first. So on the right, you see an if then else. You can think of this as a node in the BDD, right? So like here would be the literal, and then depending on whether this condition here is true, then X, the output, is the same as the then part. If the condition is false, then the output has to be the else part. So this is just an if then else, right? So you see it also here written in a different way. Okay, and that's again our SAT encoding, as I explained before. So SAT encoding of this if then else would be gate would be of this max would generate 4 clauses, and here they are. So like maybe read, like for instance, the common one would be, what if C is true and T is true? Okay, the condition is true and the then part, well, then the output has to be true as well. So let's try to find this. So if C is true, okay, C is true here, and T is true, then yes, the output has to be true. Okay. So in essence, you're kind of giving the 4 cases where sort of data propagates from the inputs to the outputs, and you just have to be complete on these cases. However, there's another situation. So what about if T and E are both true, right? T and E both true. Then it doesn't matter what C is. So C is then redundant, X has to be true. And the same, of course, if T and E are both false, like both of the inputs here are false, then X has to be false, no matter what C is. And these are these 2 clauses here. So here is the clause when both of them are false, then X has to be false. And here, if both of them are true, then X has to be true. And these clauses, if you check, are not part here of this 4 ternary clauses, but they are implied by this gate. And therefore, the question is, should I add those clauses to the CNF encoding because they might have the SAT solver? But actually, you shouldn't. And the reason for that is like intricate. So it's, well, first of all, you can get those clauses by resolution, right? You can take two of these clauses, resolve them on X, and you would get this clause here, and and therefore actually the SAT solver could do that too, and this is one part of interest in preprocessing or in-processing techniques, which is called ternary resolution, and then the SAT solver would do it for you. And what's the benefit of it? Well, the SAT solver would then know these clauses are redundant and therefore can be ignored in certain parts of the SAT solving, like for instance, if you want to do variable elimination, but they can be used during propagation. And further, of course, these clauses could also be just learned by conflict. So that's why, in essence, it's better not to add those clauses when you encode such multiplexers. All right. Then I'm not sure whether I should spend time on this one. So most of you should have seen it. So this is the Dimex format. So if somebody wants an explanation on that, then please stop me now. Otherwise, I go faster.
So
this is the input of SAT solvers, which is like an, yes?
I think there is a question on the chat.
Yes.
Which is asking, what is the cost of building representations such as AIG?
What's the advantage of AIGs? Did I get
what is the cost?
What's the what?
The cost.
The cost. Yeah, the cost is actually not that bad, because if you think about it, like, let's go back to the so the question was, how expensive is it to have such sort of like an intermediate level in a thing? Or I mentioned that sort of like, I told you, initial version of CBMC didn't have that. And the cost is actually not that much, because if you think about, oh, sorry, where's my picture here? So how would you represent this? Well, this thing here has two children, right? And you need a tag, and maybe like for a hash table. So actually you're happy with kind of 4 pointers or 4 words. And if you really want to save space, you can actually do 4 bytes, not just 8. So you could have like one AIG node in 16 bytes. Well, then you need to have the hash table 50, like another pointer. So maybe 20 bytes for AIG nodes. While if you think about the 3 clauses which you need for the AND, right? So we have it here. This was the 3 clauses for the AND. They would use far more space. Like, well, in KeySAT, I think like these two would each of them also be in around 20 bytes. So we have already 40, and this here would be way more. So it will be in the range of 40 bytes. So space-wise, there's not actually, these AIGs are sort of like 1/5 of the CNF you would generate out of them. However, and that's the real drawback, is software engineering-wise, they're complicated. Why are they complicated? Well, because I didn't show you this, but actually we're going to have here also back errors all the time. And these back errors kind of happen in kind of incremental usages of an SMT solver. There's no real in-processing yet in SMT solver. This is actually an interesting open question, but like some forms of in-processing where these back errors are used. Like for instance, if the SAT solver down here finds that sort of like something is true, like a unit is true, right? The formula implies the unit. Then you can propagate this back to the encoding phase. You can propagate it over the AIGs. And that makes it really complicated to maintain this whole thing. I don't explain it in this talk, but like my student Katalin and I, Christoph Scholl, had a paper last year at the SAT conference where we sort of simplified some part here. Actually, it's like this arrow here is simplified a lot here by a new way of doing incremental solving. The encoding, let's say the encoding becomes much simpler. So that's kind of the real problem with the cost with these AIGs. That sort of, you add here another layer, this layer, and you need to somehow get this back arrow here working, and that's painful. Does this answer your question?
So,
yes?
I mean,
Was it more like, what's the benefit of these AIGs? And so I don't know. Like maybe it was more the question, what's the benefit?
Yeah, I think Ravi, who asked the question, is.
Yeah, so the benefit is.
This answered my question in great detail. Thank you very much.
Okay. So the benefit is, like, just short for those who want to follow up on that, like with AIGs, you can do structural hashing, like you find isomorphic graphs, like things which are identical, which on CNF is really tricky. So I think like I have like 5 papers on this trying to do this, but it's like way slower finding, for instance, isomorphic circuits in CNF than doing it with an AIG, where it's trivial to just read the file, put it in the hash table, and you have it.
Armin, there is another question from Srivas. I guess, Srivas, you can unmute yourself and ask.
Yeah, I will do that. Yeah, can you go back to the slide where you showed the site and encoding for if-then-else?
Yep.
Yeah, I mean, you made a comment that...
This one?
No, if-then-else. Later, much later. I mean,
if-then-else.
If-then-else, correct.
Yep.
Yeah, this one. Now, I understood that these constraints, additional constraints, can be learned, can be inferred. That part I understood. But you said that adding them would be harmful. I mean, I don't see why adding them would be harmful, except that they'll be increasing the size of the encoding. Is that all, or will it have other impact? I don't.
Yes, so we have the other impact, which is really subtle, but like I cannot.
What is that impact?
I cannot completely explain it here, but we'll later in the second session, we'll talk about preprocessing, and there's like something which is variable elimination, which is really the most important one we still have today. And there, you really, when you eliminate the variable, you need to take all clauses in which it occurs into account. However, you can ignore the redundant ones, which are implied by the formula. This is actually not that trivial to see. Like our paper, our in-processing paper from 2012 was exactly about that. Why can you ignore these sort of learned or redundant clauses during variable elimination? And you can. And therefore, it's good to mark these guys as redundant, because then you don't need to use them when you do variable eliminations on any of these like X, C, or E. You can just ignore them. We only need to sort of do variable elimination with these guys. That's the argument. Okay, then, all right. So there's an API. And I hope some of you have seen this or used this, because this is really sort of the usual way how people use SAT solvers. Actually, it's very funny that, for instance, the best symbolic execution systems like CLE, for instance, they, for instance, would still not use a programmatic interface when they talk to SMT solvers. They don't use an incremental call. And the reason is related to what I explained before, because of all these green back errors we saw. And that's just not trivial from the engineering perspective. However, on the SAT level, people are more comfortable in using APIs. And there is a standardized API, and I'll just show it to you. And this is like sort of like formalized in this form of a graph from the API of PicoSat, which I wrote like maybe like 15 years ago. And the reason for that is manifold, and we can discuss this also, why particular this. And it's like, well, at least this picture is pretty symmetric, which is nice. Okay, so you can maybe remember it, but let me explain what's going on here. Okay, when you get a new solver, then you're here in this unknown state, and then you add actually clauses. So the way how it works is you add individual literals actually, and then you terminate a clause by adding 0. So this is very similar to the to this Dymex format, right? So you kind of read this, you add like -1, you add 2, you add 0, then you have the first clause. In addition, you would allow assume. So this is a single literal, and it says this thing should be assumed for the next SAT call. For the next SAT call, which I will do by going here from this state to that state, then the solver will solve, right? Then this assumption has to be satisfied. So the solver here would make sure that any the search space is restricted to these assumptions, and therefore it would go here after finishing. So these are these dashed errors, either to unsat and sat, and that means if it goes, for instance, to sat, then all these assumptions you made here, all these units you assumed, will be satisfied, and you can query the assignment of these individual literals. Again, let's go back to the example. So like here we queried the value of the variable 1. Well, it's false because I'm not wearing a tie, and the shirt is true, so I'm wearing a shirt. And this querying the 0 and 1 status of the model can be done here, right? But while it of course doesn't make sense to ask for value when you're in unsat mode. Okay, and then if you want to do another query, then this is triggered by just adding new constraints or new assumptions. Also note that these assumptions here, they only hold for the next solve call. They're forgotten. So this was a design decision. And it's true for most applications that you want that. It's not true for all of them, like you have a stack-based calls to the solvers, but then you just have to assume it again. Okay, you can be also interrupted here. And also, what about unsat? Well, if you're unsat, then you're sure that under these assumptions, it's not possible to find a model of all the clauses, okay? But then you could ask, and this is this failed call, which of these assumptions were actually were required um, lead to this situation that the constraints are not satisfiable, the clauses are not satisfiable. And then you get them back. So you could ask them, like here, it's the same API as above. So you would ask value of a literal, and it's either like true or false, actually minus one or two or one. So I got this wrong one time. It was not, and if it failed, it's the same. So you can ask, was this particular assumption necessary? And this is called like a core-based reasoning. So this way you get a core out of your assumptions. And then in addition, if you're putting sort of assumptions to all the constraints you kind of interested in, whether in the core, you also can get sort of a clausal course or a constraints course. And this is used in many, many applications. And here's like how you would use it from C. So I'm not going into details here. This is almost a complete set. I think there's like one more function added recently by Tomasz. So Tomasz and I came up with this sort of formalization. And basically the blue part here, these are just C symbols. And you can really take sort of a dynamic library. And with the SAT solver, you don't know anything about the SAT solver. And the SAT solver just needs to implement these blue library functions. And then, of course, implement this model, this API model I just described, and then you get a SAT solver. You can connect it to anything. Okay, here's the Cadigal version, where Cadigal is a C++ based tool and also has a C++ API. So that's why this looks like C++, or it's C++. All right. Okay, that would close my my encoding part, which like I'm 10 minutes over, but like I think that's okay. Are you other questions on encoding? Otherwise, I'll move on to kind of the real core solving part. Other questions? All right, then. Then maybe to the things where I actually assume that most of you know already quite a bit about, because I was told like many of you have been to previous tutorials and you've seen like CDCL in classes. So I have to admit, this also happened to me, just as maybe as a joke. So I was invited here in Austria to another like place, to a seminar, and I was doing my standard sort of like CDCL introduction. And then after the talk, people said, yeah, so it was a nice talk, like 45 minutes of this. Well, actually, we're teaching it all the time in our classes, so this was not new. And I fear the same will be true here. So that's why I plan to go here extremely fast. And you really need to stop me if I jump over things which are already known. One thing I should add here, which is a historical story here, is that these solvers here, DP and DPLL, which we're going to discuss on the next slide, they are usually traced back to papers from the 60s, like 61 and 62. But actually, there's like a report on this project, which was sponsored by the NSA, actually, which is from 1958. So we should really say this dates back to the 50s, not to the 60s. And this report became actually public, so it was never completely secret, because it's in essence what's written in these papers. And a couple of years ago, we got hold of that one. And it's very funny to read that, because it's really like much longer than the papers. And for me, most interesting is they already had like a discussion on algebraic reasoning in this original technical report, which did not make it into the published journal version. So anyhow, we should really say that these go back to the 50s. And then many things happened since then, and I'll talk about some of them. Okay, DP procedure. This was the first paper, Davis Putnam. That's very simple. So you have like, you eliminate variables. So for those of you who know about Fourier-Motzkin, it's exactly the same thing. So you take a variable, you take all the constraints in which it occurs, and then you kind of resolve out, you project out that variable. And then there are two base cases, and these are like satisfiable and unsatisfiable. And usually, well, when I saw this it took me like hours, and even on the second day, actually Yunchan explained this to me the first time. I could not really get my head around it, but now I've been working with SAT solvers for more than 20 years. It's completely trivial for me. But let me just spell it out once for those of you who are in the same situation as I was like 20 years ago. Well, if you have a CNF and the CNF is empty, that means it's true because we have a big conjunction of ends. Then, well, the formula is satisfiable. If you have a CNF and there is a clause in it which is empty, which means an empty disjunction, that's false. Well, and then you have and false, so this this false propagates and makes the whole formula false, and then it's unsatisfiable. Okay, these are the two base cases which most of us take for completely granted, I hope, but at least I struggled with that like 20 years ago. Anyhow, so if this is not the case, then you find at least one variable in the formula, and then you can project out that variable. And in CNF, this works by adding all resolvents on X, and then you have, like, the resolvents don't have X in it anymore. But now comes the interesting part. Then you remove all clauses in which X and not X occurs. The same is true for Fourier-Motzkin. So you take like all constraints which have which are upper bounds for X. So you would have X is some upper bound, and you take all the constraints which are lower bounds for X, right? And then you end up with lower bound is equal to upper bound. You do it in all possible ways, and that's exactly the same what we do. But now the interesting part is that you, so this is Fourier-Motzkin on real constraints. But now in Fourier-Motzkin, you're now allowed to remove this this line here. And that was actually not formally justified in the original papers. And it's also not that it's not that simple actually, because you need actually a strong argument why you're allowed to remove those variables. And maybe the reason why people were not that much interested, because they were only interested in refutations. And if you're only interested in refutations, so that you only get to this line, you're not, you don't need to sort of worry about that, because these clauses will just stick around. The crucial part here is what about if you have the formula becomes empty, nothing is left, then the formula is satisfiable. Now the real practical problem would be, how do I get back a model for that formula? And yeah, we have lots of sort of work on this. So Google for reconstruction stack, which then gives you this argument why, if the formula is empty, you can go back. It's kind of the completeness of the completeness of the DP. And in practice, it gives you models, right? That's the important point. And it became, of course, important here in this preprocessing here, because, well, if you use this DP for preprocessing, and at the end the SAT solver says, yes, satisfiable. Think about like if you use it for some security problem, right? And then the SAT solver says, yes, there's a bug. You can break this. But well, then the user would ask, yeah, but please give me back a sort of the maybe key or something. Well, then the SAT solver implementer would say, well, I don't know how to get a model. That would be bad. And therefore, if you use preprocessing and thus bound variable elimination, you actually need a way to if in this case above here, you're satisfiable to get back a model while dropping these guys here. If you don't drop them, that's fine, but then the preprocessing would not work. Okay, now back then they figured this would actually eat up all their memory. I think they were, yes,
Armin?
question? Yes?
Yeah, I just had a comment. So this, so when it is satisfiable, when you require a model out of it, which is what the practical applications do require, then this is not really a decision procedure, right? It's not just a yes, no.
Yeah, exactly. You're completely right. So we struggled with this also with the paper we published this year at each card. So the question, so what's the, not many people looking at that, like the problem um, if you don't not only want to have yes and no, but you also want to get back a witness. So I think we did not completely sort of nail it down. So you can check out the paper with Lee Barnett and David Cherna, what we wrote about. And also if you look into the literature, we were struggling to find good citations for this problem. So the problem is, give me back also a witness. And this occurs exactly in this context, what we're just discussing. And it's like the paper this year was about redundancy notions, right? And there, in these redundancy notions, we might come to that later. There's a witness, and this witness is exactly such a thing which you want to get from a SAT solver. And so it's not just enough that the SAT solver says, yes, satisfiable, but you also need to get the witness. And this problem is different than just satisfiable. Let me put it this way. Does this answer your question?
Yeah. Thank you.
So DPLL, I think I don't need to explain that one. This is usually even better known. You have the two base cases exactly the same. So what's new here is some kind of, you can think of this as in-processing, but it's not really in-processing. So it's just sort of some deriving some immediate facts. It's called Boolean constraint propagation. That's kind of the most important part in SAT solvers, also the most expensive one. And then there's this recursive call. So I skip that. And here would be a DPLL example on all the 8 clauses with 3 literals. And therefore, if you recall from before, from the introductory example, this thing is unsat. So that's why we will have here like 8 cases where, 4 cases where it's unsat. Why only 4 leaves? Well, because we have this BCP. After assigning A and B to true, the first clause, like A and B is true, then C has to be false. So we get this without a decision. So this is why this doesn't have another child. Okay. And this happens all the time. And then we get here to a clause which is false. This is the red one here. This is DPLL. Okay, now Zhao and Karen came up with this conflict-driven clause learning. Actually, the name conflict-driven clause for learning is to Ryan, last name I forgot all the time, like a student from David Mitchell who implemented the Siege SAT solver, which was one of the best SAT solvers in the early competitions. And he came up with this term in his master thesis, and it's very cool. And that's why people actually use this term, and also Joao and all the others accepted it. One reason why we're so happy about this term is because it's different than DPLL, right? And it took a long time to convince the SMT community not to talk about like DPLLTs. There's like a famous paper by Neuwenhuis and others in the communication of the ACM, which is DPLL, but this is not true. What they're actually doing is CDCL T, because with the old DPLL, it would be way harder to implement an SMT solver. In particular, these lemmas on demand fits the CDCL, but not the DPLL. So doing these lemmas on demand from theory solvers with DPLL is actually pretty difficult. And yeah, but that's how history goes. So nowadays they should have called it, of course, CDCL. Okay, and but if you go back to what their insight was, and I did some historical research on that, there was already some ideas on learning no-goods in the constraint programming community, so learning clauses. However, they would not keep those clauses. They thought like keeping these clauses would be too expensive. So what people did in the constraint programming community was to throw away those clauses immediately. They also had already back jumping in it, which is also like sort of very nicely covered by this work by Joao. But they didn't have this idea of implication graph. At least the papers I checked didn't have an implication graph. So that's why I'm going to explain next. So in my view, the really groundbreaking thing there was this implication graph, and sort of like keeping these clauses, which will also mean that actually sometimes you have to throw them away, but more about that later. And that's also a very cool insight, are these unique implication points, which are pretty technical, but they're also start to make sense only if you have this notion of implication graphs. So let's have a look at first how CDCL works, and then on this implication graph. So same first branch as before, there's no different, but now the yellow part here is different. So you would learn the clause, which in this situation is just the negation of the decisions A and B. And then if you look at that, you realize, okay, if I would have known this clause when I made this decision, then this decision would not be a decision, because this clause is a unit clause, right? So if A is true, then this clause here says B has to be false. So that's why this would not have happened. So you're kind of fixing what you did, and that's why you actually make this decision A, but you're not doing the decision B, but you just propagate its negation. And then you get into this conflict, and then also something's happening, which happens quite often in SAT solvers. Actually, we'll later see this maybe in a demo. It's this that we're having here. The only decision here is, of course, false. And then you see, like, we would not even have made this decision. We first need to propagate this A. No, sorry, this A, not A. Okay, so we're propagating then this unit A here. Now it's became pink. And then we still need to do a decision, because we have ternary clauses, and just making one unit doesn't help anywhere. So we're making a decision not C, and then we'll get another propagation, and then we get here this conflict. But we still made a decision, so we have to learn the negation of this decision. So like C, and then we add this clause, C to the formula, and then we have these two learned units, like not A and C, and by those two we trigger this B here in this green clause here to be true here, because A is false and C is true, then B has to be true. But this is in conflict with this red clause here, and we're done. So then we look at the sort of decisions, and we have none. So in some sense, we're collecting all the decisions, a big OR of all the negations of all the decisions, but well, there is none. So we get actually empty, and we add this clause to the formula. And during this whole process, we made sure that all these added clauses down here, this 1, 2, 3, 4, are implied by the formula, including this empty clause at the end. And because of that, the formula is unsatisfiable, because it cannot, like anything which implies false is itself false. Okay, so this is how CDCL works, and I think you saw this before. Now let me, maybe before we go to the break, show you something, this implication graph, and also this minimization. So here's implication graph. There's like two main notations mixed, but let me just first explain the notation. So for instance, we just saw that units at the top. So like there was a not A, actually not an A, but like let's assume we have a unit A equal to 1 at decision level zeros. So this is our root level. Knuth prefers to call it root level. So maybe I should change top to root in this picture. And at this root level, you have this unit A, okay, and also unit B. Then we have different decision levels, like I separate them by dashes. So when you go to the literature, people don't draw these dashes, but I like this a lot, because this is how it's really organized in the solver. So all these things are sort of on the trail of assignments after these guys, and then these guys here are after these guys. This is after that one. So you can think of this as also as a partition of the trail of the assignment stack. So that's why I like this picture much more than like people would draw in tutorials and in the literature sort of arbitrary graphs of this. And then you have to figure out by looking at this @ sign, like the corresponding levels. While of course, in my notation here, graphical notation, I keep everything which is at decision level 2 here in this layer. And therefore this @ thing is redundant, but I keep it sort of to make the connection to the other way of drawing these implication graphs. Okay, so this sort of explains the layout, but what about the arrows? So here's like a clause which forces T to be true. So this clause has three oncoming, this literal here has three oncoming edges, and all of them here, D, G, and S, imply that T has to be S. So this clause, of course, if you pay too attention, what I explained before is just that clause here. So not D, not G, not S, and T. Okay? And we can do this for every sort of such node here. And in particular for this last one, for this conflict, this is like uh, kind of an artificial node, and it's called kappa. So I asked Joao actually, because I gave a tutorial last year at the SAT conference, at the summer school at the SAT conference, and then Joao was in the audience, and I asked him why he called it kappa, because that's not the Greek letter for C, it's the Greek letter for K. And his answer was, he used, well, I'm not sure it's true, but he claimed in the audience that this is because in German it's conflict, while in with the capital, while in English it's conflict. But I think this is just a coincidence, and he just picked this letter K by chance. So anyhow, so this is an artificial letter, and you need to think of this is all these incoming literals on the edges as a source of these incoming edges cannot be true at the same time. So Y cannot be true with the Z. This, of course, corresponds again to this not Y and not Z. Okay, so you now saw like these two cases, and now how does conflict analysis work?
A question here.
Yes, please.
Yeah, you have shown as though that, I mean, you've shown every level being here, but that is not generally true, isn't it? I mean, you could, not every conflict might need to be dependent on decisions made at every levels.
Yeah, exactly. This is what this example will actually show. You will see it actually in a minute. This
okay.
is
So, but I thought you said that you would keep track of every level. No, not that is not what you meant. Did you? I mean, you would.
I mean, like in the solver itself, you would really have this graph, and you would actually have it partitioned in these levels. But of course, like now when we do the conflict analysis, and that would maybe not pull in some levels. This is exactly the point of this example. You will see in a minute.
But I guess my question is, does SAT solvers keep only partial, implication graphs by skipping levels, or I guess it has to keep the entire implication?
You need to keep all of them. Also, by the way, there's like work on chronological backtracking, which came from Intel in 2018. Then my student and I formalized this a little bit more clearer a year later, in also last year. And there it's if you want to mix get a mixture between DPLL and CDCL, you can chronologically backtrack, and then suddenly you will do this out of order. Then this picture will actually not hold anymore. You will have, like on the assignment trail, you will have things out of order. Like there could be a literal with a decision level lower after literal with a higher decision level. But that, like, you need to read those papers, and I will not touch upon this in this tutorial. So it's getting more complicated with this thing, actually, if you do this called chronological backtracking combined with CDCL. Okay, now what conflict analysis does, it can be explained here by looking at these two clauses, right? So the blue clause, so the blue area with the pink letters corresponds to this pink clause here. And then the conflict we looked at it, and then they overlap here in this Y, right? Like in this is the sort of the consequence of this implication for this hypergraph edge, while here this is an antecedent, and because of that it occurs here negatively in this clause here and positively in that one. So I can resolve these two. And by the way, all these literals here are true, right? And because we always sort of flip it because of this implication, like here T is flipped, right, to false here. in the clause, these guys are all false except for this thing which is implied. This one is true. While in this clause, in the conflict clause, everything is false. And therefore, we're resolving over y and not y. Remember, y was the only literal here in these two which was true. And here all of them were false. So that means the resolvent, which is the next line, is again all literals false. Okay, and I continue doing this now. So this corresponds to this cut here. Actually, this conflict analysis can also be seen as finding a cut between the conflict node here and these decision nodes. All right, so now I can continue with this clause. And this one here has all literals, you see the clause here corresponds to negation of this cut here. And it has all of them false. And then we could either take this T or that Z. I think I take the T first, yes. And then I have the clause we also looked at before. And this clause here, it only has the T true and the rest is false. And then the other one has all its literals to false. And if we resolve these two on the T here, well, this literal, the only true one gets thrown away, and we get this yellow cut here, which corresponds to this clause here. Okay. Then we do it with a Z. This is a binary. Yes.
Why the I is included? I mean, why just why the cut doesn't stop at H? Why you need to include?
Yeah, I come to that in a minute.
Okay.
So the reason what we're doing here is we continue resolving here literals on this last decision level actually, and I'll explain this in two more steps why we do that. So here's clear, right? So we take the Z and take it out actually, right? So we take the Z out and replace it by X. That's kind of what this resolution does. We get this cut. And then at the end, where we remove here this X, replace it by S. But wait a second, this S is already, this would be this clause here, this pink line here corresponds to this clause. This S here is already in the resolvent, right? So we're removing this X and replace it by not S, but this S, not S, is already in the resolvent. So actually we're shrinking just this clause. So we, from this clause here, we get to the consequence by just dropping the X. Oops. And that's something we call, sorry, I only have it here on this slide, self-subsuming resolution in preprocessing. So it's a resolution where the resolvent here subsumes one of the two antecedents. And if you think about this, this really has to happen if you do what I just said and what was the question. So I just take the lowest decision level, right? And I resolve literals. Actually, I need to do this in topological order. And at one point, it has to be the case, at the latest here at the decision, that only one literal is left from this decision level. Okay, in this resolvents we produce. But now it happened actually earlier, right? So we didn't do, you see, we didn't resolve this binary clause which is behind here. We could do that. And I have a slide where we do it. And that's actually way better to just sort of get to this literal here, which, so the first situation where like only one literal on the last decision level is left. Okay, why? Well, because think about it. Now this clause by the construction is again false in the current situation. And it contains exactly this literal here. The only one here on this decision level 3, right? So I put down the decision levels here, right? So D is 1, G is 2, and H is also 2, and I as well. Okay, so that means if you think about it, if you would have been even on decision level 2, oh, yep. This is 4. Sorry. Not confusing. Oops, wrong pencil thing. This is 4. So at decision level 3, I should not have done this because you see this would be implied as S, but it goes even further. Even on decision level 2, That's why this is called here back jump level. If I would have known this clause here before, I should have used it for propagating not as. Okay, so I would have put here somehow not as at this decision level here. And you also see the effect, and this was maybe like the reason for your question is there's 3 is missing here. There's no 3 here because we jump over, this is redundant here, this decision. So we're really jumping back from decision level 4 to decision level 2. Okay, and why is this good? Well, if you would continue, which is of course correct, right? You would just resolve one more step. You would get this clause here. This is called the decision clause or last UIP clause. It also has the property that it has only one literal left on the decision level. So let me try. So this is now 3, R is 4, and the others were 2, and this D was 1. But because of this 3 here, which we pulled in, right, we can only backtrack to this level here. And that's not as good, right? So that's why these UIPs are really useful, and they help you to sort of like cover up the bad decisions at the end. I want to go briefly over the minimization now, and then I would do a break. So if you go back to our first UIP clause, right? So this is the, so note here, first UIP clause after 4 resolutions. And now if you look at this situation here, you will realize that actually I could resolve away this I. And the cool thing about this is this is again a self-subsuming resolution, right? If I make this resolution, then I need to add this not H here, but this not H also occurs here. So that's why this clause is kind of a subset of this clause. So I kind of shrink this clause only. And that's always good because getting a stronger clause, right? Like, why should that not be better? Not be worse. Okay, so that's why I get this clause. And that's like immediate, like we call it actually local minimization. But we can do more. And here, this H here, it does something bad in a sense. If I resolve against the reason of this H, then I will pull in this E, which was not in the clause, right? So here I get the resolvent with a E, which is not in the clause. However, if I then do some graph search, so I'm searching kind of here backward, I figure out, this E can also resolve away by taking something which is a unit, which goes away anyhow, and a literal, which is already in the graph, right? Which is this not D. Okay. So like here, not D, and the B goes away anyhow because it's a unit. So that's why I can actually remove this H. And I get this clause. And this is after minimization. And that's a very important technique. So this would give you sort of a 20% to 30% less smaller clauses actually. And also helps not to confuse the solver that much. That's sort of my intuitive explanation. So you get shorter clauses. That's good for memory. But like these clauses are also more focused, and that seems to help the solver. So you also get less conflicts by doing so. Okay, so I think like I'm 10 minutes, 12 minutes over time. It would be good to do a break now and maybe also have the questions after the break, right? Maybe ask the organizers. I could also do questions now. I don't mind.
I think let's probably take a 15-minute break, but maybe if you'll be around, then you can still answer questions. So
okay, let's do that. Okay.
Yeah, I guess. So let's meet at 3:30 Indian time. This is GMT plus 5:30. So please convert to your time zones.
Mm-hmm.
There's the Discord channel also where we could Discord rooms.
With the recording.